Okay, welcome back. In this video, we are going to state and prove the mean value theorem, which is really just Rolle's theorem when the world shifts, right? If it starts tilting. So in our last video, we said, okay, if you have some function, which, okay, it's continuous and differentiable on this interval a, b, and if you know that the value of the function is the same at both the start of the interval and at the end of the interval, then you know there is somewhere in between where the derivative of the function is equal to 0. So what if we drop this assumption that the value of f is the same at the beginning and the end of the interval? That's what the mean value theorem is going to be about. So now I'm going to assume that maybe f of a, say, is up here and f of b is down here. So that's when we have a and that's when we have b. So all I've really done is taken this floor and said, well, what happens if things get shifted? Well, in this case, instead of having a flat line, which has slope 0, right? And if we go back to Rolle's theorem, you say, okay, look, I have this nice dashed line here, has slope 0. And the claim, right, was that there was some point in between the endpoints where the slope, the instantaneous slope, right, the instantaneous rate of change, right, this is also a slope, was also equal to 0. Okay, so in both of these cases, the slope is equal to 0, or if you like, these lines are parallel to each other. That's what the mean value theorem is actually going to say, is if I now have my function and, okay, it's again going to go through these 2 points, I'm no longer going to claim that I can find some point where the slope is 0. Instead, I'm going to be finding some point where when I draw the tangent line, we missed it just by a little bit, didn't we? Okay, we'll draw that again. If I try to draw my tangent line, it also has a slope, but not equal to 0, but equal to the slope of this line going through the endpoints. Okay, so this has some sort of slope. In fact, we know what that slope is. The slope is f of b minus f of a over b minus a, or if you like the difference quotient notation, this is the a difference quotient of f at b. And the goal of the mean value theorem is to show that this, I can find some point, okay, and of course this is some c, where the slope of this tangent line, which we know is going to equal f prime of c, is going to be actually this difference quotient also. Okay, so these two lines are going to be parallel. Okay, so let's make this precise. So as before, I have a function with domain, the closed interval AB. It's going to be continuous on that entire closed interval, and it's going to be differentiable on the open interval AB. Except unlike before in Rolle's theorem, right, all these first three are the same. We don't have to assume that f of a is equal to f of b. The conclusion then is going to be that there exists some c between a and b such that the derivative at c, well, is no longer 0, which was the slope, right, of this difference quotient line, right? It's the slope of the secant line between these 2 points. Instead, right, it won't be 0, it'll just be, again, this dq. So this will be dq a f of b, or if you prefer, f of b minus f of a over b minus a. Okay, so the instantaneous slope is equal to the average slope, okay, at least at one point. All right, so how are we going to do this proof? Well, I want to quickly go back and look at the intermediate value theorem, okay, because we proved the intermediate value theorem a while back. And when we did, we used a certain technique. And this technique we're going to use again when we prove the mean value theorem, and then again when we prove the generalized mean value theorem. Okay, so here we go back when we were doing the intermediate value theorem. Remember, this is saying, right, that if we have some function f which is continuous on the closed interval AB, and you knew that, say, f of A was less than f of B. If you chose some element C between f of A and f of B, then it had an f preimage Z, right? You could find some Z that was going to map halfway in between. And the way we proved the intermediate value theorem was by taking this original function f and shifting it down, right? So we took every single value of f and subtracted this value c. And by doing that, instead of having to find some point where the graph intersected sort of this arbitrary height c, we instead could look at just trying to find where it intersected the x-axis. And because f of A was less than f of B, when we shifted everything down by c, the f of A, which was less than c, had to be negative, and the f of B, which was greater than c, ended up having to be positive, or at least when we switched over to this function g. So we ended up with a simpler situation, all right? And then we could reduce it to things maybe that we already knew a little bit about. Okay, so let's get back to the mean value theorem. We want to do a similar construction here, right? We're not going to subtract just a constant this time, but the idea is we want to subtract something from the original function so that what we are looking at ends up being the situation of Rolle's theorem. We want to get back to the situation where the beginning and the end are still the same. So the way we're going to do that is by taking this red function, and we're going to subtract away another function, specifically the blue function, okay? So there is a line here, right? In fact, we know what the slope is, and we can actually use the good old point slope form, right? You may remember that from middle school or high school. Okay, we can actually use point slope form to come up with the equation of this blue line. So for example, we know if I do y minus, let's see, we'll do f of b, or let's do f of a, that's fine, right? We'll use the point we know on this graph is the point a comma f of a. So I'll use y minus f of a is equal to the slope, which is dqa f of b, times x minus a. Okay, so this will be the equation of the secant line. Okay, that's this blue line here. Okay, and so let me solve this for y. So y is going to equal dqa f of b times x minus a plus f of a. Okay, so this is now my new, that is the equation of this line, and I want to build a new function. And so I'm going to define a function, we'll call it g, also is going to go from a, b, the closed interval, to r. And how are we going to define it? Well, g of x is simply going to be the original function, f of x, and then I'm going to subtract this blue line. Okay, so we have dqa f of b, which is just a constant, times x minus a, plus f of a. Now, what should be obvious immediately is that at the endpoints, the red and the blue line are both the same, and so this function g is going to have to be 0. So we know that g of a is going to equal 0, and g of b is going to equal 0. Okay, and this, again, just because we're defining this function g as the difference of the red and the blue lines, and at these points a and b, they intersect. So their difference is 0. Okay, but we also know that f is continuous on the closed interval AB. So here we have this continuous function on the closed interval, and the rest of this function is just a line. That's certainly continuous. Okay, so this function here is definitely continuous on the closed interval AB. In fact, it'd be continuous on all real numbers. Okay, so if I have the difference of two continuous functions, you get a continuous function. So g is continuous on the closed interval AB. And so, right, so this is one of our algebraic continuity properties. Okay, but also f is differentiable on the open interval AB. And of course, this line is differentiable. In fact, we know the derivative, right? It's just this difference quotient. This is differentiable, certainly on the open interval. In fact, it's differentiable on the entire real number line. And again, using algebraic differentiability properties, we know that the difference of these two functions is differentiable. And so g is differentiable on the open interval AB. So these are our algebraic differentiability properties. Okay, but I now have the situation of Rolle's theorem. Rolle says you have a function which is continuous on the closed interval, differentiable on the open interval, and which is identical on the endpoints. In fact, we even know it's equal to 0. We didn't need that. But by Rolle's theorem, we know that there is some point in between a and b for which this function is going to have 0 derivative. So by Rolle's theorem, there exists some c between a and b such that g prime of c is equal to 0. Okay, let me put the 0 first because I want to expand this g prime of c. So I know that g is equal to the difference of these two functions, so its derivative will be the difference of their derivatives. So this will be the derivative of f and then evaluated at c minus, well, let's see. This is just a line. The derivative is simply going to be the slope. So minus dqa f of b. Okay, but if 0 is equal to their difference, then this implies that the derivative at c is equal to the difference quotient. And that is precisely what we were trying to prove. And so the mean value theorem is complete. Okay, so this whole trick of adjusting your function so that you could think about it as normalizing it so that it returns to a situation you already know something about. This is a really handy technique that mathematicians love to use all the time. Now, before we move on to the generalized mean value theorem, I want to show you one result that maybe is the most important application of the mean value theorem. Okay, so this is going to be another theorem. And it's going to say that antiderivatives, so this is something we haven't talked about really much. So antiderivatives, this is where, right, if I have some function f, and then I take its derivative, I get f prime. And we would say that f is an antiderivative for f prime. Okay, so every function that is a derivative is the derivative of something, and that something is an antiderivative. However, it could be the case that you have more than one antiderivative. So for example, I know that x squared has derivative 2x. So x squared is an antiderivative for 2x. However, it is also the case that x squared plus 4 has derivative 2x. So x squared plus 4 is another antiderivative for 2x. Okay, how many antiderivatives can there be? Well, certainly infinitely many, because I can just add any constant I like. It turns out, though, that this is going to be the only way of building antiderivatives, because antiderivatives are unique up to a constant. Okay, and this is that whole plus c that you've learned about. Okay, so the statement here, well, let's see. Let's assume I have two functions, f and g, with a common domain, the closed interval ab. Okay, and we're going to assume that f and g are continuous on this closed interval. We're going to assume that f and g are differentiable on the open interval. Okay, so this should remind you of the hypotheses of the mean value theorem and of Rolle's theorem. Okay, if the derivatives are equal, so if the derivative of f and g are both the same for all x, in the open interval AB. Of course, I don't check the closed interval because I only know derivatives even exist in the open interval. Then there exists some constant C, so this is a capital C now, such that f of x is equal to g of x plus c for all x in the interval AB, the open interval. Okay, so this is telling me if I have two different functions, f and g, that have the same derivative, okay, which means that both f and g are antiderivatives for the same function, f prime, g prime, whatever you want to call it. Right? So if I have two different antiderivatives, then those two derivatives are the same up to this little constant. Okay, so we're going to give a proof of this, and it's not super difficult. All right, so let's let x less than y be in the open interval AB. Okay, we're going to show that the difference of f and g is constant on AB. So we're going to show that when I evaluate f minus g on x and y, I get the same value. Okay. So we know that f and g are differentiable. So f and g are differentiable on AB. Well, their difference is also. So is f minus g. Okay, so f minus g, this is again our algebraic differentiability property. Okay, now f minus g is differentiable on AB. Also, f minus g is continuous on AB, right? So maybe I could have done this in the other order here, right? These are continuous on the closed interval AB. Fine. Why do I want all this? Well, because I want to apply the mean value theorem. So by the mean value theorem, well, actually, let me before I apply the mean value theorem, okay, let's note it's differentiable on the entire closed or open interval AB. But if I look at x, y, right, I don't know exactly where they are, but maybe there's x, maybe there's y. This is a subinterval. Right? Take the open interval or the closed interval, doesn't matter. This is some subinterval of AB. And so if my functions are differentiable and continuous on the entire interval, then they must also be differentiable and continuous on the subinterval, okay, just between x and y. So I can apply the mean value theorem not just to the entire AB interval, but even to this subinterval xy. Okay, so that's the key here. So by the mean value theorem applied to f on the interval xy, right, we have, well, let's see. It says there's going to exist, so there's some c in between x and y, not between a and b, right, but between x and y, such that the derivative of f, or not f here, but actually I should say not applied to f, but applied to f minus g, so same thing here, f minus g, is equal to, well, we want the difference quotient at the start point, which is x, of the function f minus g evaluated at y. Okay, now let's write this out in full, right? So this would mean that, let's see, the difference quotient will be f minus g applied to y minus f minus g applied to x divided by y minus x. Okay, and what is this f minus g prime of c? Well, the derivative of the difference is the difference of the derivatives. So this would be f prime of c minus g prime of c. But we had an assumption. We assumed that f prime and g prime are the same everywhere on the interval AB. So if I subtract f prime and g prime, I'm going to get 0. Okay, so I have 0 is equal to this fraction. But when a fraction is equal to 0, that means that the numerator is equal to 0. So this implies that the difference of f minus g at x and y is equal to 0. And so now that implies that f minus g at y is the same as f minus g at x. So I've taken two arbitrary elements between a and b, and I've evaluated this function f minus g at those two elements, and I get the same answer. That tells me that f minus g is constant on this open interval AB. Okay, well, what does that mean? That means that f minus g is equal to some c, right, on AB. Okay, or if we add g to both sides, f is equal to g plus c on AB. Okay, and that's what we were trying to prove. So any two antiderivatives are going to be the same up to a constant. So mean value theorem, really, really important for this. All right, okay, so we will see you next time when we prove the generalized mean value theorem by using the mean value theorem.